let's start with something what I hope is straightforward. That last time we spoke, we were talking about the contact forces. The normal force, the tension force, and resistive forces. And of those, we only discussed two: friction and drag. Now, a few things that you should probably already know, but in case you don't, let's make sure they've been covered. That when we talk about force, the unit of force is the Newton or the pound. We won't use pound. That is the English standard unit of force. A pound is a stone foot per second squared, but we will use the Newton, which is a kilogram meter per second squared. Something that is different about physics than a lot of other sciences is that our units are very much rooted in only three things: kilograms, meters, and seconds. The MKS system. So almost all of our units are some combination of these three things. And although there are a few other units that you should know, on your exam, it's these three. A lot of times what we're going to do is we're going to derive something that's going to be, when we're done, it's going to be a bunch of letters. Those letters all have a unit associated with them. You should always check your units to make sure they make sense and represent what you're trying to find. So knowing that something that is in a force has units of Newton doesn't mean very much, but knowing that something that's kilograms meters per second squared is your solution, that should be telling you that your solution represents a force. And that's why I want to be very careful. I also know that you know this because F equals MA. And that's really where it comes from. Mass, kilograms, A, meters per second squared. But F equals MA isn't a law. And that's where we need to be a little bit more cautious. Net force equals MA. That's a law. That's Newton's law. But F equals MA, not a law. There are lots of forces out there that do not cause accelerations. Newton's second law isn't about a single force. It's about all of the forces that act on an object. And therefore, Newton's second law is powerful only when reminded that we're dealing with net force. The word net force means the sum of all forces. That's what the word net means. So I'm not going to remind you of that very often, but I will say the word net force when I mean the combination of the forces acting in a system. And it's not minor. Look, you guys are in E&M. So when you're being asked about forces, when they say net force, be careful. Net force probably is less about actually adding forces together and more about figuring out how the object behaves under those forces. For example, a sprinter goes from rest to 12 meters per second in a displacement of 10 meters. If their mass is 60 kilograms, what's the net force acting upon them? I'll be willing to speak to this again. So a sprinter, 60 kilograms, goes from rest to 12 meters per second in a displacement of 10 meters. What is the net force acting upon them? I'm sorry, it was what? I just couldn't hear you.
The net force is 432 newtons.
Perfect. Thank you for the assistant there. Perfect. 432 newtons. Now, for those of you who don't know what you were supposed to do there, and I know there's a few because I can see it on your faces, I gave you all motion equation stuff. So I wasn't trying to actually try and trick you up. I was trying to make sure you realized that this is not really a force question. This is an exercise in plug and chug. Could you realize what you needed to do was find the acceleration from the kinematics information and then use that to determine the net force? It's not really a particularly interesting question. Textbooks love this question because they can ask it about 5 dozen different ways. So they can ask you if the force was this and the acceleration was that, what's the mass? And if you have this force on this mass, what's its acceleration? They're boring questions. They're not interesting. However, this also doesn't really tell me what was happening to the person. Name a force that was acting on the person. Friction, sure. What direction should I have drawn friction if I wanted to draw the force acting on the person? And be careful, folks. You're going to get this one wrong, and you're going to be asking about this for a while. But friction does not act on this person to the left. Friction acts on this person to the right. Now, I'm afraid a lot of you don't know why that's true. However, think about it for just a moment. I mean, there's nothing else to push the person forwards, but they're trying to take their foot and drag it backwards against the floor. Their floor, therefore, must be pushing forwards on their foot. And the only force that could do that would be friction. Name another force that's acting on my person. All right, drag. Should I draw that as a bigger bigger force or a smaller force than the one I've drawn here? So I'll put drag like so. Name another force acting on this person. I heard just mostly mumble, but I'm going to say gravity. When I draw this force, I'm going to point out that I believe the gravitational force of weight is greater than the frictional force propelling them forwards. So I'm not drawing it haphazard. I'm going to draw it in such a way that it is larger than the other two forces because I believe it is. Now I know this is not the only forces acting on the object. There's at least one more. What is it? That's right. When I draw that force, I'm going to be careful to draw it the same size as the weight. And I'm going to do so because I don't believe my person is accelerating up or down. I believe the ground is capable of keeping them from sinking, and they're definitely not floating off into space. So these are, I believe, 4 reasonable forces that are acting on the person, with friction being greater than drag. Now, knowing that the net force is 432 doesn't tell us very much about what's actually happening to the person. It does let me know that these 4 forces must combine to produce a net force, a total force of 432 newtons, if my person is going to accelerate in this manner. Does it really display what the individual forces are doing? No. But I know more than just this. I know that the weight is about 600 newtons. I know that because we define weight as mg, which shouldn't be too big a surprise. This would be the net force of an object that is dropped. Think about it for just a minute. If you drop an object, a rock, and the only force acting on it was gravity, the weight, then the net force would be equal to ma. But we know that all things near the surface of the earth fall at an acceleration of about 10 meters per second squared. So I would say that the weight would equal mg is a result of applying that idea. This is not an expression for how gravity works. It's a statement of what happens when you drop an object. Let's understand that they're different. Gravity requires something called the universal law of gravitation if you want to really study gravity. But if I want to discuss something's weight near the surface of the earth, this will do. It's how something falls. All right so far? So that also tells me that I think the normal force is 600 newtons. I know that because I believe the net force in the y direction is 0. So I believe the ground pushes up with the same amount of force as the weight pushes into the ground. Ultimately, it's these two that sum to give me 432. They're imbalance, which tells me that the frictional force must be greater than 432 newtons. Again, great, that doesn't tell me enough. But I can discern all of that from our short discussion just now. Now, hitting the first is that a free body diagram begins with a dot that represents your object. That we draw arrows in a manner consistent with each of the forces that may act on our object. I would encourage you to always start by asking about any fundamental force that may be acting upon your system. In this class, the only fundamental force we will worry about is gravity. At the same time, we will then go through the contact forces, starting with any surface that has to be in contact with our object. It must be applying a perpendicular force to the surface that acts on our object. We'll ask if there's any surface sliding with respect to another surface. If so, there's likely to be friction involved. Friction must be perpendicular to the surfaces in contact. Friction must be parallel to the surfaces in contact, but perpendicular to the normal force, which means this is a hard perpendicular. I would always ensure that you draw it as perpendicular as possible with ruler when you're using your, when you're doing your test. Drag, on the other hand, is a force that opposes velocity and will always be directed in opposition to velocity. That does not have to be the same direction as two surfaces. When you're drawing your free body diagram, the expectation is that you will draw the arrows in such a way as they portray the size of the force. I roll called the forces from you. You guys started with friction. However, when you're doing these on your own, especially when you start, I would always encourage you to start your first force as gravity. Let it dictate the size of the other forces. Very often, gravity will be a good measure of the respective size of the other forces. So in order to see that play out, I would like you to consider the inclined plane question for a moment. If I have a box at rest on an inclined plane, could you please sketch out what the forces are that are acting on the box? When you're drawing a free body diagram, from this point forward, from today forward, a ruler should always be on your desk. Now, I'm not saying to dive in there and grab one. You've got 2 or 3 minutes till the bell rings. But on the AP exam, if they ask for a free body diagram, you could be looking at 4 to 5 points on that particular question. These are the points you must get. Do you understand me? That's going to be the gimme question right there. So we get these points every time. And what I mean by that is, in pop quizzes, when you don't get these points, you'll hear about it from me. Does everybody understand? You've got to get these. And that means a little more than what it meant last year. Generally, they'll ask you to draw your free body diagram someplace away from your object, which I would almost always encourage. But I want to draw it right on the object because I have a point to this. First, I would encourage you to draw the gravitational force first. Let it guide the size of your other forces, but it should be a straight line that is directed towards the center of the earth, which means find your horizontal and make sure it's perpendicular to it. Now, we know this object doesn't move, which means there must be equal forces left and right and up and down. When I go to draw the next force, the normal force, don't do so arbitrarily. Keep in mind that the normal force must be perpendicular to the surface. But the size of that force should be drawn in such a way as to give you scale for the normal force. I'm sorry, scale for the frictional force. I said normal force, I meant frictional force. What I mean by that is I drew this arrow not in an arbitrary way. I knew it had to be shorter than the downward force of gravity, because I know that the frictional force will also be pulling up on it at that angle. So when I'm going to draw these, one of the things I'm trying to do is look at how much of each of these forces is upwards. Those blue lines represent how much of each of the forces are aligned with that dotted line. And I think the combination of those should equal the downward force of gravity or be close to it. While at the same time, there should be a left to right balance in the size of the components that are pushing left and right. Which means when I drew this, I tried to draw it in such a way that there was balance to the respective size of gravity, with gravity being the one I drew first. But use a ruler, be considerate. They're not going to measure your arrows to see if they're perfect, but it should look at least that good every time. And you should be considerate of the relative size of all the forces. But I will hammer home the fact that this had better be a hard right angle. Okay? So this is a solid free body diagram. It does all the things I want it to do. And it conveys to the reader, you have an understanding of the interaction of those forces. In this case, that the net force is equal to 0. All right.